Welcome to Lesson 5, Networking, the layer you'll spend more time debugging than any other in production Kubernetes. The whole system rests on one promise. Every pod gets its own IP, and every pod can reach every other pod directly. No NAT, no port juggling. That flat network is what makes K8s feel simple from an app's perspective, but underneath it's three components doing the work: a CNI plugin moving packets between nodes, kube-proxy translating service IPs to pod IPs, and CoreDNS turning names into those service IPs. Knowing which of the three owns a failure is the difference between a 5-minute fix and a 5-hour outage. So here's the map for the next 40 minutes. Structured as the SRE loop you'll run every time the network misbehaves. First, we observe internalizing the three IP spaces, pods on their CIDR, services on theirs, nodes on the host network, all routable. Then we diagnose by picking a CNI that fits the workload. Calico, Cilium, or Flannel each make different trade-offs. We act by understanding kube-proxy modes, iptables, IPVS, or eBPF, and when to switch. And we document the DNS path through CoreDNS, because most service-unreachable tickets end up being name resolution, not routing. Before we touch any CNI plugin, internalize these 4 rules. They're the contract Kubernetes makes with every workload you'll ever deploy. Every pod gets a unique cluster-wide IP, and pods talk to each other directly. No NAT, no port mapping gymnastics. 3 distinct CIDRs stay in their lanes. Pods owned by the CNI, services programmed by kube-proxy, nodes living on your underlay. And Rule 4 is the one that trips people up at 3 a.m. A cluster IP isn't bound to any interface. It's a virtual IP, and iptables or IPVS rewrites the destination to a real pod. If a packet looks like it vanished, it didn't. It was DNS'd. Now, who actually implements those 4 rules? That's the CNI plugin's job, and you've got 3 names that cover 90% of clusters in the wild. Calico routes with BGP, no overlay, mature and boring in the best way. It's the default you'll see in kube-admin and most distros. Cilium uses eBPF in the kernel, gives you the highest performance and deep observability through Hubble. That's where production at scale is heading. Flannel with VXLAN is the easiest to stand up, but it has no NetworkPolicy support, so keep it in the lab. Rule of thumb: Calico to learn, Cilium to scale, Flannel only when policy doesn't matter. Once the CNI gives you a flat network, kube-proxy is what turns a cluster IP into an actual pod on the other end, and you get 3 modes to do it. Iptables is the default, but it adds a chain per service. So lookup is ON, and somewhere past a few thousand services, your nodes go CPU-bound, just processing packets. IPVS flips that to O1 with a real kernel load balancer, scales cleanly to 10,000-plus services, and gives you round-robin, least connections, source hashing. And then eBPF, Cilium replaces kube-proxy entirely, runs the logic in kernel with no iptables overhead, and hands you the deepest observability story of the 3. Iptables to learn, IPVS to scale, eBPF when latency and visibility matter most. Which brings us to the third piece of the stack, CoreDNS. It runs as a plain deployment in kube system, and Kubelay auto-injects its cluster IP into every pod's resolve.conf, so any lookup for web.default.svc.cluster.local resolves to a service IP that kube-proxy then translates. Watch that n.tor5 setting, though. It means short names get tried against every search domain first, so a single external lookup can fan out into 5 or 6 queries. When people say the cluster is down, 9 times out of 10 it's actually DNS. So let's stitch all 3 components together and trace one curl from pod A to pod B. CoreDNS resolves web to a cluster IP. The packet leaves pod A, hits the node's iptables kube services chain, where kube-proxy's rules DNS it to a real backend pod IP, picked at random from the endpoint set. Then the CNI takes over for the node-to-node hop. Calico via a BGP route, Cilium via an eBPF redirect. 6 steps, 3 components, and every step has a command you can run when it breaks at 3 a.m. Now that you can trace the full path, here are the 6 reflexes that turn debugging from guesswork into mechanics. Start with DNS. Hence lookup from inside the pod, because 70% of so-called connectivity bugs are really CoreDNS or resolved.conf issues. Then kube-proxy get endpoints. Empty list means your service selector doesn't match your pod labels, the single most common bug in Kubernetes. If endpoints look healthy, curl the pod IP directly to bypass service routing. That one test splits a CNI problem from a kube-proxy problem in seconds. On the node, iptables TNAT-L or IPVS ADM LN shows you what kube-proxy actually programmed. Hubble gives you flow-level visibility if you're on Cilium. And when every abstraction lies, TCP dump on the node never does. Pin this one to your wall. 12 patterns covering the whole stack. Kube-proxy get endpoints, get pods, O-wide, and ends lookup for the service DNS pod triangle. Iptables, IPVS ADM, and IP route for what kube-proxy and the kernel actually programmed. TCP dump and kube-proxy debug node when you need ground truth. And on the CNI side, the mental shortcut. Flannel is easiest. Calico is the sensible default. Cilium is the fastest. 2 CIDRs to remember, pod and service. And you've got the whole networking layer in one screen. Now the failure modes, 5 mistakes that pattern match to most networking outages I've seen. 1 and 2 are CNI owned. A pod CIDR that collides with your VPC will give you intermittent connectivity nobody can explain, and running 2 CNIs means 2 things: programming iptables, which is just chaos. 3 is policy. A flat open cluster is one compromised pod away from lateral movement everywhere. 4 and 5 are CoreDNS. 2 replicas don't survive a 1,000-pod cluster, and when DNS breaks, always start at the pod's resolve.conf before you blame the service. Theory's done. Now you build the muscle memory. 3 exercises, and they're not optional. First, trace a packet end-to-end on a multi-node kind cluster. Watch DNS resolve, find the kube SVC chain in iptables, then TCP dump the packet, leaving one node and arriving on the other. Second, break a service on purpose by mismatching the selector. That's the bug that pages someone every week, and the reflex you want is kube-proxy get endpoints first. Third, read the kube-proxy rules and CoreDNS logs while queries are flowing. After these 3, you know exactly where to look when curl is slow or DNS times out. And that's networking, traced from the flat network model through CNI, kube-proxy modes, and the CoreDNS path. Tomorrow we shift from how pods talk to how they remember. Lesson 06 is storage, persistent volumes, claims, storage classes, and the CSI drivers that make stateful workloads possible. Run those 3 exercises tonight, and I'll see you at the persistence lecture.